Hey, geographers, and welcome to another session in our geography lecture series. I am your lecturer, Donovan Rattray. Today, we're going to be looking at wave action. Now, under this topic, we're going to be looking at the nature of waves and how they operate, as well as how waves actually use their energy and the features that they produce as a result. So, let's get right into it, shall we? Well, first of all, let us look at some key terms. For example, swash. The swash is the plunging action of the wave as it rushes onto the beach. That is, when the water is washing up on the beach, that is what we call a swash. However, when the wave is going back or running back down the slope into the water, we call it a backwash, which is the returning of the wave towards the sea. Let me show you what I mean. So here we have the waves coming onto the beach. The wave as it is coming on the beach, and the water is coming on the beach like that, that is what we call the swash. So here we have the swash coming in. Alright, this is the swash coming in. So the water coming in from the sea is the swash. Now as you can see, the water is going back towards the sea. The water going back towards the sea is what we call the backwash. So when the water is coming in from the sea onto the beach or onto the shore, as you like to call it, that is what we call the swash. So here's the swash coming in. There it is. The swash is coming in. Now as the water now is beginning to go back into the sea or going back to the sea, that is what we call the backwash. Alright, and these two processes or these two movements of the waves are very important in the features that are formed along the coast. But we'll get deeper into that as the lesson progresses. Here we have a photograph. Here we have a photograph of a wave. Alright, and as you can see, the wave is coming in, and that is what we consider to be the swash. Now let me show you something, class. Up here are the top parts of a wave that you see coming over. The top part of the wave is what we call the crest. And when the wave gets too high, the crest begins to break or plunge. So, as you heard, waves can break. So how do waves break? Well, waves break when they move onto very shallow water. When the wave is breaking, water starts to move forward. When the depth of the sea is less than the height of the wave, this is what happens. Friction with the bottom of the wave increase and the wave begins to move slowly. The waves bunch up because they are moving more slowly. And then the pattern of the water circulation begins to change. Becomes, instead of becoming perfectly circular, becomes more elliptical. The front of the wave becomes steeper, and as it becomes steeper, the crest of the wave begins to move forward much faster than the bottom or the base of the wave, and then it begins to tumble over or tumble forward, and this is what we call the wave break. So basically, students, what they're saying here is that as the wave is coming towards the shore, because it is encountering the shallow part or shallow seabed, it begins to slow down because of friction. And as it slows down, because the top part of the wave is moving faster than the bottom half of the wave, it begins to rise or pile up, begins to get taller. When it gets too tall, as it is continuing to move forward, it then moves forward and then breaks or plunges. So you see the water, the top part of the crest, the white the white top part of the wave begins to now tumble over, break or bend or tumble over into the water or into the or onto the beach as it is coming in. And that's what we call a wave break. So here's a diagram showing what we're talking about. So right here, as the water is approaching the shore, all right, you can see it's deeper here. So because it is now approaching the shore, friction, it encounters friction down here on the seabed. So that causes the wave now to slow down. However, as the base of the wave is slowing down, the top part of the wave is still moving, but moving a little faster. Now, instead of having a circular motion, it now begins to change into an oval or elliptical motion instead of a circular motion, because what is happening is that now the bottom of the wave is slowing down and the top half of the wave is getting faster. So because it's moving faster, it is now rising. Now as it begins to rise and continues to rise, the bottom half again coming into more shallow area begins to interact more with the seabed down here. And this causes it to slow down even more while the top part is still moving fast. So as it is getting taller and it is moving too fast, it moves forward. And as it moves forward, it begins to bend. And this now, you find the wave now crashing or plunging, or what we say breaking, as it is plunging down. All right, and that is what we call, that is how the wave actually breaks or plunges. Here we see it in action again. We can see here that the wave is moving towards the shore, and as it is moving towards the shore, the motion of the water begins to change from a perfect circle to an ellipse, to an oval or elliptical shape, because the water is now rising and because the bottom half of the water is beginning to slow down due to making contact down here to the sea floor. It begins to slow down, but the top part is moving fast, so it's going to start to move forward and then plunge, as you can see it happening right here. All right, so that is how the waves break. And you see that every time when you are at the beach. It's just that this is the mechanics of what really happened. As you can see with this assimilation, the wave is rising and it's now plunging because it is moving, the top part of the wave is moving faster than the bottom half of the wave. So as it is moving faster, it means that now it begins to rise and then come forward and then plunge or drop or break right down into the water. That is what we call breaking. That is how waves break. Let's see another example. So, waves approach the shore. So you see, students, whenever the waves are approaching the shore, you don't see the wave. You might, maybe based on where you're standing at the beach or along the coast, it looks like the wave is actually coming to you straight ahead. But if you look carefully, you realize that the wave is not really moving directly towards you. All right. What happened is that the wave is actually coming towards the beach at an angle. It actually curves or turns as it is coming towards the coast. All right. So when the wave begins to change direction or curve as it is coming towards the coast, this is what we call wave refraction. It is refracting. It is not coming to you perfectly straight. It's actually turning or curving as it is coming towards the coast. And that is responsible for some of the coastal features like headlands or even the production of or the creation of caves along the coast in the headlands or even arches. But these are features we're going to see more. Now, besides the waves refracting, the waves also move parallel towards the coast. Now, these waves that move parallel towards the coast are what we call longshore drift. Some books or in some sources you will see the term oblique waves. It's the same thing. So when waves are approaching the shore, waves don't just come towards the shore directly or in a straight line. No, the waves actually turn or curves as it is coming towards the shore. And this is what we call wave refraction. And at the same time, while the waves are refracting, you also have the waves moving parallel or beside or alongside the coast or coastline. And these waves that are moving parallel to the coastline or next to the coastline are what we call longshore drift. And they are responsible mainly for the formation or the extension of coastal features like beaches or tombolos or spits. And once again, we are going to go deep into these topics as we go further into the lesson. So here is a diagram. This is the diagram showing you what we mean by wave refraction. As you can see, shown by the arrow or the arrows, the waves, as they come towards the shore, they actually turn. All right, they're actually turning. They don't come straight. They actually turn or change direction. And that is what we call wave refraction. They actually curve or turn as they are coming towards the shore, as indicated by the arrows. And that is what we call wave refraction. And they are the ones responsible for the creation of some of our coastal features. Here we have another um, angle. So as the waves are coming in, look at just watch the arrows. As the wave is coming in towards the shore, it is actually turning. So when you're at the beach, for example, or standing along the coast somewhere, everyone, it looks to you like the wave is actually coming directly at you from way out. But if you look carefully, you realize that the wave is actually changing direction or coming at a particular angle, coming to you from a particular angle or curving. That is what we call wave refraction. So the changing of the wave's direction as it is turning is what we call wave refraction. And that is how they actually approach a shore. But along with that too, waves approach a shore. Waves approach a shore in a parallel way, in that they actually move parallel to the coast. And when they move parallel to the coast, that is what we call the longshore drift. But here you can see it in motion. As the waves are approaching the shore, they are actually turning, they are curving. All right? They're changing direction as shown by the arrows. And that is what we call wave refraction. Now class, as you can see everyone, there's a photograph showing wave refraction. You can see the waves or the ripples in the water. And if you look carefully, the waves are actually changing direction. They're turning. All right? And that is what we call wave refraction. So it's a photograph showing you how the waves are refracting. Longshore drift is the process by which sediments are transported by waves along the shore. They are sometimes referred to as oblique waves, as we said a while ago. Let me show you again. So here we have a diagram showing longshore drift. As the water moves up along the beach, it tends to push particles at an angle because the longshore drifts, here have them, the longshore drift is moving in this direction. So the lighter shading of blue is the longshore drift, is the wave itself, or the longshore drift moving parallel to the coast in this direction with the prevailing wind. And the prevailing wind is the wind that is blowing from a particular direction, and it is pushing the wave in this direction, the longshore drift. Now, as the wave is moving up onto the shore, it carries sediments at an angle like this, and then take back some of the sediments back to the sea. And it will take them back up, move some more, and as it is continuing to go in that direction, it brings it up like this and then down as the water is going back. So as the swash is going onto the beach, the backwash will take back some of the sediments like this. So they move up, down, like a triangle. Again, here we have the wave or the longshore drift moving in this direction, carrying particles in this direction. As the swash comes onto the beach, it carries particles, and then the backwash will take back some of the particles. The swash will take them up again, the backwash will take back some. And here we have it continuing. So the backwash will take them back to the sea, and the swash will put them onto the shore, and that is how they move. But let's try and see if we can be a little bit more clear on this one. Okay, now geographers, here we see waves approaching the beach. Now the longshore drift is taking materials onto the beach by the swash, and the backwash is removing the materials. Now as the longshore drift follows the prevailing wind further up along the coast, the swash will put materials onto the coast or onto the shore, and the backwash remove it back to the sea. Again, we can see where the longshore drift is moving further up the coast with the swash taking materials onto the beach and the backwash removing it. So here is it once again, the swash carrying the materials up to the beach, and the longshore drift is now taking it further down to the beach, down further along the beach because of the prevailing winds. And here we have the backwash removing the sediments. As it moves further along the beach, the longshore drift carries the sediments, and the swash brings it onto the beach, and the backwash removes some of it back to the sea. So basically, class, that is how the process of longshore drift works, and that is how it actually transports the materials along the beach. So let's look at this one last time. There you can see the materials being carried further along the coast, and the swash brings it up, the backwash takes back some. And as the longshore drift continues to move parallel to the coast further down the coast, the swash brings it up to the beach, and the backwash takes it back to the sea. So class, here we have an aerial view of the swash, and as you can see, the water looks cloudy, right? Well, that cloudiness is caused by the sediments that the water is bringing onto the beach, and that is how it actually works. The waves bring the sediments onto the beach by the swash, and the backwash will take back some. But if you look carefully, here we have the longshore drift going in this direction. So materials are actually being transported up and along the beach. If you look carefully, here they are moving in this direction. See, there they are. So here you have the longshore drift moving in this direction as the swash is moving up the stream, or should I say up onto the beach, and the backwash is coming back with some of the sediments into the sea, and all this sediment is being carried along the coast by the longshore drift. That is why the beach is as long as it is, because the longshore drift constantly moves the sediments along the coast as it is moving parallel to the coast. And as it is moving along the coast with the sediments, the swash is bringing the sediments onto the beach, and the backwash is going to take back some so that the longshore drift can continue to carry them further along the coast, continuously extending the beach. Now, everyone, we're now going to move on to the different types of waves. So far we understand how waves actually break, how they approach a shore, and we understand what is wave refraction. So let us look at the different types of waves. There are two types of waves. The first one are the constructive waves. Now, constructive waves are basically spilling breakers which fall forward as they break. The front of the waves is usually steep and the wavelength is long. In other words then, the space between, or the distance between two waves is quite far. That's what we mean by the wavelength. All right. Now the waves build the beach because constructive waves build beaches. The reason for this is that the swash will carry up more materials in a constructive waves. Now, there may be at least 6 to 8 waves per minute, so they are not very fast moving waves. All right, they move very slow because there is a long, or a very long wavelength between waves. All right, in other words, then the distance between two waves is quite long, and for an entire minute you may have about 6 or 8 waves approaching the shore. They are not very tall and powerful waves either. They are gentle in terms of how they approach a shore. Here's a simulation of a constructed wave. As you can see, the waves are slowly moving towards the shore as they go up the beach. Now, as you can see also, the distance between one wave and another wave is quite long. That's what we call a long wavelength. Alright, let's try now. Okay, so now we move on to the next type of wave, which are destructive waves. Now, destructive waves are basically the opposite of constructive waves because they are what we call the plunging breakers, where the crest of the wave cuts, or should I say, curls forward over a large air pocket and then vertically downwards. These waves erode the beach. Yes, they erode. They actually remove the materials because they have a very strong backwash and a very weak swash. So the backwash carries more materials down the beach than the swash had carried up. All right, so the backwash is very strong, and that is the reason why they remove materials. These waves have steep profile, they're short wavelength. In other words, then students, the distance between two waves is very short, so much so that you tend to have the swash of one wave actually colliding with the backwash of another wave. And that is what we mean by a short wavelength. And they move very quickly as well. So in about a minute, you can have anywhere between 10 to 14 waves approaching the shore. Here we have a photograph of what a destructive wave looks like. They're very high, they're tall, they're quite um, intimidating when you do see them. Here's another one.
Destructive waves are very powerful and much bigger than constructive waves. As the name implies, these waves they destroy the coastline. They actually erode the coastline because they have a stronger backwash and a weak swash. As you also can see, they're much more forceful and also they are very fast. If you can look carefully, the backwash of one wave actually collides with the swash of another. This means that the waves do have a very short wavelength, and you can expect anywhere between 10 to 14 or even 16 waves per minute striking the coast. So as you can see, destructive waves, bigger, powerful, weak swash, strong backwash, and they erode the coastline.
Now, we're going to delve in the realm of how the waves actually use their energy. The waves use their energy in three different ways. Waves erode, waves transport, and waves also deposit. Let's look at how waves create, or should I say, waves carry out the process of erosion. Yes, along the coast we have erosion by the waves. One process is known as corrasion or abrasion, and this is basically where the waves actually takes rocks or mainly rock materials and hurl it or throw it against the cliff face or against the coast causing these rock materials to erode or remove materials. Waves also causes rocks to collide against each other, collide and smash against each other. And over time, these rocks will become rounded and irregular shaped at times, right? This process is what we call attrition, and it's basically where the waves or the power of the waves actually takes up rocks and causes the rocks to clash or collide against each other. And over time, these rocks will become rounded and smooth and irregular shaped. And that is the reason why when you go to the beach or along the coast, you will find irregular shaped rocks that have that are round and smooth and flat and of different kinds of shape. All right, that is all caused by years of constant attrition of these rocks out there along the coast. The sheer power of the water can force air into the cracks along the coast, especially against cliffs. When this happens, the air pressure that is forced into the cracks or the openings in these cliffs causes the cracks to expand and over time force the rocks to break apart. This is what we call hydraulic action, and it is the process by which the waves, the power of the water, is used to remove rock material by simply crashing against the cliff. And as it crashes against the cliff, it forces air into the openings of the rocks, and the pressure that it exerts causes the rocks to actually expand or break or split open even wider. And over time, as this process continues, it will actually cause the rocks to break apart. Right? So that is hydraulic action. Finally, oh, and that is the reason why sometimes when you go along the coast, you hear um, you hear crackling noise or even explosions along the coast, and that is hydraulic action actually taking place right there. That is a great evidence to show you that hydraulic action is actually taking place along the coast. And one place I can recommend to you to go to actually experience this is along the coast of White Horses in St. Thomas, Jamaica. For those of you who are out there in other countries, when you do manage to come to Jamaica, just put White Horses, St. Thomas as a part of your itinerary. And for those of you who really are looking a nice area to carry out your field study on coastal features and processes, White Horses in St. Thomas is a great place to be, because you're going to go there and you're going to actually see all of these processes taking place, and you're going to hear the rocks exploding and cracking. All right, so this is a nice place to go to see all of this happening, especially hydraulic action. Corrosion or solution. Note, don't mix up corrosion with corrasion. Corrasion, remember, or abrasion is where the waves utilize rock debris and throw them against a cliff, using it to carve out or to erode the cliff face. But with corrosion or solution, it's basically that the water itself is acidic, and this tend to be more effective along limestone coast, where because the water itself is acidic, it is what we call carbonic acid, and it's acidic because it has um, other minerals in it like salt and so on, and even carbon dioxide. Now what happens is that this weak acid tends to erode the limestone cliffs. So it actually dissolves the calcium in the rocks by changing the calcium to calcium bicarbonate. And that is what the water now will remove from the cliff in solution or being dissolved. So that is what solution or corrosion is all about, where the wave, the water itself, erodes the rock by dissolving the limestone or the calcium carbonate in the rocks, by turning it into calcium bicarbonate, and thereby eroding it in solution, dissolving it, all right, thereby eroding it by solution or corrosion. So here we have a demonstration of where the wave is taking the rocks and throwing them against a cliff, creating an opening with these rocks. That is what we call corrosion or abrasion. It's using the rocks to actually carve out the cliff face, all right, creating what we call a notch at the base of the cliff. And we're going to see this further as we go deeper into the lesson. But look what is going on right here. The wave is actually taking up the rocks right here and clashing them against each other. The same rocks that it's using to carve out the cliffs is clashing them against each other, and they're breaking up. All right, that is what we call attrition. So attrition is taking place in this illustration as well, and this illustration explains both attrition and corrosion, otherwise known as abrasion. Hydraulic action. So hydraulic action, everyone, is where the water is now forcing, using its power and forcing air as it collides or clashes with the cliff. It forces air into the rocks. And this air that is being forced in the rocks, the pressure is so great that it causes the rocks to break apart. And over time, as this process continues, it breaks apart and the rocks fall off. Hence, we have the process of hydraulic action taking place. So once again, it's where the rocks, or should I say the wave collides with the cliff face, forcing air into the cracks, causing the cracks to expand, and over time you'll have the rocks breaking off the cliff face. So here we have hydraulic action being illustrated in a diagram. Here we have rocks that have been eroded by corrosion or solution. So this is what the rocks look like when they are being eroded by solution or corrosion, because the water itself is a weak acid, and because it interacts with the calcium in the rocks, it turns the calcium carbonate into calcium bicarbonate, thereby removing this calcium bicarbonate in solution. So you tend to have these little rounded pockets or irregular shaped hollows in the rock along the coast. Rock types are influenced by erosion when along the coast you have alternate layers of hard rock and soft rock. Now the hard rock are resistant to erosion. They take a much longer time to erode. They don't erode so quickly. And then the soft rocks are easier to erode by wave action, so they are quickly eroded over a period of time. The band of hard rock that stands out after the soft rock has been eroded form what are called headlands, while the soft rocks that are carved out next to these layers of hard rock form bays, and it is within these bays you have beaches being formed. All right, so basically that is how rocks are influenced by erosion. All right, or that is how rock types influence erosion. You're going to have a layer of hard rock and soft rock along the coast. And the soft rocks are going to be quickly eroded over a period of time to create bays, while the hard rocks, which are what we call the resistant ones, they take a much longer time to be eroded because they are more resistant to the processes of erosion along the coast, and they will form what are called the headlands. Good example of this is Pico Tenerife in Barbados, and you will also find other examples of this throughout the Caribbean. Another way by which waves use their energy is transportation. And waves transport in four ways. Traction, where the wave actually drags large materials along the seabed. These materials, or should I say, these rocks are too heavy for the waves to lift, so they will actually roll them or drag them along the bed or the seabed. Saltation is where, those rocks that are not too heavy to be lifted but are still not light enough to be carried in along the water or to be floated in the water. They're actually just bounced on the bed because they're not as heavy as the bigger rocks that are rolled or dragged by traction, but they are light enough to be picked up and hopped along the bed of the sea. So they are actually bouncing along the bed of the sea by the water or by the waves. All right, and that is through saltation. Suspension is where much lighter materials like sand, for example, are carried or floated in the water. All right, so that is how they are carried. They are actually floated or carried in the water. They are not dragged along the bed. They are not they're not bouncing on the bed. They are very light, so they'll be carried all the way. They'll be floated in the water. All right, that's what we call suspension. They're suspended in the water. And finally, dissolved load, where the materials that have been dissolved or the rocks that have been dissolved are carried in dissolved load. All right, they are very difficult to make up because they are very tiny particles because they are dissolved load. But that is another way by which the waves actually transport their materials. They can transport them by dissolved load. So they will dissolve the materials and carry them in the water. So those are the four ways by which the waves transport their materials: through traction, where the materials that are too big and heavy are either rolled or dragged along the bed of the river. Saltation is where the materials that are not as heavy but not light enough are actually picked up and bounced or hopped along the bed of the sea. Suspension is where the much lighter materials like sand are carried in suspension. They are suspended in the water, so they are floating or carried by the water. They are floating. So sometimes when you're at the beach, for example, and you stand in the sea, you can actually feel the sand beating against your skin because it is carried in suspension. And dissolved load are those minerals that have been dissolved in the water and are carried in the water, like the salts, for example, or calcium that have been removed from limestone cliffs. All right, that is what we mean by the way in which the water or the waves transport their load. Here's a demonstration of that. Now everyone, here we have a demonstration of what I was explaining a while ago. So down here, let me get my laser. All right, so down here, we have the heavier materials being dragged or rolled along the seabed. And this is the process of traction. And then we have those lighter materials that are light enough to be picked up but are still too heavy to be carried all the way. They're hopped along the bed and that is what we call the process of saltation. Here you can see them bouncing. And then up here now, we have the finer particles like sand, for example, or clay, other sediments being carried all the way by the water. They are suspended or floated in the water. And that's what we call suspension. And those minerals like salts and calcium that have been dissolved in the water are carried in solution. All right, and that is the reason why, for example, the seawater is so salty, because what you're tasting is the salt in the water, and the salt is actually a dissolved or a dissolved solution. That is why you can't really see the salt in the water, but you can actually taste it. All right, so we want to see what are the different features formed along the coast. And you have basically two types of features formed along the coast at any given place, any given time. We have features that are formed by erosion and features formed by deposition. But right about now, we want to see what are the various features formed by erosion. Some of these features are easy to be explained because they actually coexist. So the formation of one will actually lead to the formation of another. And we're going to get right into what I just said a while ago. That sounds profound, doesn't it? The formation of one will also lead to the formation of another. So let us see what I'm talking about right here. Now we're going to look at the first coastal features to be created by erosion. The first that we have here are cliffs and wave-cut platforms. Remember I told you that the creation of one will lead to the formation of another? Well, this applies to cliffs and wave-cut platforms because as the cliff is being developed, the wave-cut platforms are also being created or further developed as well. And I'll explain what I mean. Now, at the base of the cliff or the bottom of the cliff, the waves tend to attack the cliff. And as it attacks the cliff, it will erode it by either hydraulic action or corrosion or even corrosion or solution, right? Depending on the rock type that is there. Either way, as the wave continues to attack the base of the cliff, it will create an opening at the bottom of the cliff. As this opening gets deeper, and by the way, this opening that is being created at the base of the cliff is what we call a notch. Some sources will call it a niche, N-I-C-H-E, right? But we call it a notch, N-O-T-C-H. This notch will actually get deeper, and as it gets deeper and gets deeper at the base of the cave, at the base of the cliff, the overhanging cliff becomes too heavy to be supported. So over time, the cliff face will collapse. As it collapses, it will create a wide area at the base of the cliff. This wide area of debris is what we call a wave cut platform. Now this process of carving out a notch will continue. It will continue. And the more it continues, the more the process repeats itself. So you have the cliff face now collapsing again. What is happening is that now the cliff face is getting shorter or going further back inland. While the cliff is continuously being developed, the debris that are left at the base of the cliff will continue to spread out and form what we call a wave cut platform. So the further back the cliff goes, right, the wider the wave cut platform gets. Now, one thing I want to be clear about where the wave cut platform is concerned, everyone, is that the wave cut platform tends to be visible at low tide when the water is at its lowest level. it tends to be visible at low tide. It is not visible at high tide when the water level rises. All right, so just to make that clear. But there is usually a wave cut platform at the base of the cliff. Why? Because as the cliff continues to break off and recede further inland, and the wave cut platform will get wider. And that is why I say the development of one will lead to the development or the creation of another. And that is why we have wave cut platforms and cliffs side by side. So here we have a diagram showing our wave cut platform is formed. So this is the level at which the sea constantly attacks the face of the cliff and creating an opening right here. This opening is what we call a notch. As the notch gets deeper, the overhanging cliff face gets too heavy and it will just break off. And as it breaks off, the cliff gets shorter and go further inland. This is what we call the cliff being retreating or receding. It's getting further back, it's retreating. All right, so as the process continues, it breaks off and it gets shorter, or it retreats, and it's continuing right here again. So this eventually is going to break off. Now while the cliff face is breaking off and retreating, down here at the base of the cliff we have a wave cut platform being formed, and the further back the cliff goes, the wider the wave cut platform gets. So the wave cut platform is only visible at low tide when the level of the water is at its lowest, but it's not visible at high tide. All right, so remember, this is a zone at which the waves attack the rock, right here at the base of the cliff. All right, and as I said, it can use hydraulic action and corrosion and even corrosion in the process of eroding the rock, creating the notch. As the notch gets deeper, it's going to collapse, cause the rocks collapse under its weight. The rubble is going to create what we call a wave cut platform down here. And the further and the more the process repeats itself and the cliff continues to go further back, you're going to have a wider wave cut platform. Now, good. So here we have a cliff face that had been eroded, and because it has been eroded, you have the rubbles down here spreading out and forming what we call a wave cut platform. So the cliff used to be right here, but because of constant attacking down here, a notch has been created, and over time the cliff face breaks off, and then it continues to recede, gets shorter, and down here now the materials spread out to form what is called a wave cut platform. So that is the reason why we say they go hand in hand. Let's go a little deeper. So here we have our wave cut platform right here, and we have our cliff face right here. All right, and you know how that worked out already. So you know that this is at low tide where the water is at its lowest, so you can see the cliff face as well as the this thing here, what we call the wave cut platform. When the water level gets very high at high tide, you will not be able to see it.
Wave-cut platforms and cliff coexist with each other. In other words, the formation of one leads to the formation of another. Destructive waves constantly attack the base of the cliff face, over time creating an opening known as a wave-cut notch. As it gets deeper, the cliff face collapses under its own weight, thereby creating what we call a wave-cut platform at sea level. The cliff face continues to recede as the process continues to repeat itself. Hence, the wave-cut platform gets wider.
So here we have cliff as well as a wave cut platform being created down here, and this is basically along the coast of Great Britain. And if you look at the type of rock, it's actually a limestone rock. So you're gonna have not only abrasion happening there or hydraulic action, but you'll also have solution taking place there as well. Next feature, caves, arches, and stacks. All right. Another case of the creation of one leads to the creation of another situation. All right, so let's get into now. Okay, everyone. So due to abrasion and hydraulic action, breaking waves tend to create fissures or openings or joints in the rocks, and over a period of time causes these joints or fissures in the headlands to open up and get larger to form what we call caves. Now, as the process of erosion continues, you'll have caves being formed on both sides of the headland, and they will be continuously eroded until the caves are tunneled through and they meet upon each other. So to the point where you can actually see right through from one end of the headland to the next. This is what we call an arch. Now, as the arch continues to get further and further eroded, it gets too weak to actually stay together with the headland. So the top of the arch is going to eventually collapse or break away and fall into the sea, leaving the headland on one side and a pillar of rock standing isolated in the sea. That is what we call the stack. Now, the stack will also be acted upon by the processes of erosion and may even get smaller. This stack that becomes much smaller is what we call a stump. So here we have the process of wave refraction. Remember that? Wave refraction, where the water actually attacks the coast at an angle, so it is curving. Well, here you have it happening right here on both sides, and it will actually act upon the headland on both sides, creating a cave. Now, because you have a cave on both sides, the cave on the other side is also going to be tunneled through continuously until both caves meet. When they meet, you can actually see from one end of the headland to the other, and this is the feature we call an arch. Over a period of time, as the process of erosion continues, the arch gets too weak, or the roof of the arch gets too weak, and eventually collapses into the water, leaving the headland on one side and an isolated pillar of rock on the other. This isolated pillar of rock is what we call the stack. And as you can see here, the stack is further broken down or eroded, and it is given the name stump.
Due to a combination of abrasion, hydraulic action, and solution, caves are hollowed out in the headlands along the coast. As the erosion process continues, the caves are hollowed through, creating what we call arches. Due to continuous erosion, the arches become weak and collapse under their own weight, leaving an isolated pinnacle or rock standing in the sea known as a stack. A smaller stack is what we call a stump.
So let's look at some caves. Here we have one. That's a cave right there, and it's basically at the base of a headland. Interesting how powerful waves can Here's another one at the base of a headland, another headland. There it is. Anybody can tell me what we call this feature right here? All right. I know you got it right. Good. That is what we call the arch. Okay, that's the arch. Now, when the roof of the arch breaks, we have this, a stack. And over this side here, we have a headland. Here we have another stack again right here. And over here, we have a headland. And usually, when the stack is continuously eroded and gets smaller, we call it a stump. All right, everyone. Next thing, bays and headlands. Again, we have a combination. Now, remember I told you earlier and showed you how rocks influence erosion along the coast? Remember I said that along the coast you may have layers of alternate layers of hard rock and soft rocks, right? Now these alternate layers of hard rock and soft rocks are going to be under constant attack by constructive waves, or should I say destructive waves. They are going to be attacked by destructive waves, and these destructive waves are going to easily erode the layers of soft rocks, creating an inlet along the coast. Now, these inlets that are created along the coast are what we call bays. Now, the layer of hard rock next to the bays that are projecting out to the sea are what we call headlands, because the headlands are actually made up of a layer of hard rock, so they are more resistant to erosion. So when you have the layers of soft rock being constantly eroded to create bays, then you'll have a layer of hard rock next to them that projects out into the sea, known as headlands. And that is how both headlands and bays are formed, because the layers of hard rock and soft rocks are constantly being attacked by the destructive waves, all right, through the various forces of erosion or processes of erosion to create the bays or the inlets along the coast. And the layers of hard rock that are now projecting out into the sea become what we call the headlands, because they are more resistant to erosion. Here we have a diagram illustrating that. We have a layer of weak rocks or hard or soft rocks, and we have a layer of hard rocks next to them. All right, and they are now constantly being attacked by the waves. Over a period of time, the soft rocks are eroded completely. All right, are eroded significantly, I should say, to create inlets along the coast. And these are what we call the bays. And the layer of hard rocks that are still there are what we call the headlands.
Along the coast exists a band of alternate layers of hard rocks and soft rocks. Due to constant attacks by the destructive waves over many years, the layers of soft rocks are constantly eroded, forming inlets along the coast known as bays. The band of resistant rocks that stand out are what we call the headlands. Hence, along the coast we have bays and headlands.
So here we have a diagram showing bays and headlands. Again, alternate layers of hard and soft rocks being acted upon to create both features. So because you have the bays being carved out, that inlet is what we call a bay, but the projecting feature next to them is what we call a headland. Here we have a headland over here. What do we have inside here? A bay. What do we have right here? a headland. We have another bay right here. And right here we have our headland. Now we go on to coastal deposition. So we have completed looking at coastal erosion, and we have looked at cliffs and wave cut platforms. We have looked at cave stacks and arches and stumps. We throw that into it as well. And we also looked at bays and headlands. All right. So now we're going to be looking at depositional coastal features. In other words, then features formed by deposition. And basically what we're talking about are materials being laid down or placed to create features. The first one we're going to look at is the one that you're most familiar with, beaches. So beaches, otherwise known as bayhead beaches, because beaches are usually found along the head or front of a bay, right? So beaches or bayhead beaches, what they're properly known as, are formed when constructive waves, remember those waves that move slower, they are not as powerful, but they move slower, and they're lower waves, right? Gentler waves, I should say then. So these are formed when constructive waves deposit sand and other material within the bays between two headlands. Good example of this, Old Harbor Bay. Love that place. Good quality fish. Yep. And that is in Jamaica. And you have Maracas Bay in Trinidad.
A beach has three main parts: the foreshore, the berm, and the backshore. The foreshore is the zone of most active change. It is the sloping portion which may vary from a few degrees to as much as 30 degrees. This slope is dependent on both grain size and wave energy, which are also interdependent. Strong wave action, such as found on exposed coasts, washes out the finer sand particles, leaving only coarse sand and a steep beach. Stones and boulders are often present on such beaches. However, on more sheltered coasts, finer sand is deposited, a gently sloping beach results. The berm begins at the high water level and is the transitional area between the foreshore and the backshore. Except on very flat beaches, the berm has a well-defined crest at the seaward edge, formed by material deposited by storm waves or very high tides. The backshore, which is behind the berm, varies in width and character. The sands of the backshore are generally fine-grained and well-sorted compared to the foreshore. Here, dunes are formed when wind force distributes grains inland.
Now, as you can see from that snippet, you can see where the beach was created as waves carrying sediments, all right, and depositing them along the bay. And that's how beaches are formed. And you also realize that beaches have at least three parts. You have the foreshore, which is the part you normally see the water interacting with. Then you have the backshore, but between the foreshore and the backshore, you have what is called the berm. All right, and these are usually there because during high tide you have the berm being created, more sediments being carried, more heavier, bigger sediments. You have sand dunes being formed there, and then behind that now you have the backshore. All right, all of these are the three parts of a beach. But you also realize too that a beach doesn't have to be a deposition of fine materials like sand. They can also be pebbles or rubbles. So not all beaches are have sand. Some beaches have rubbles as well, or rocks. All right. Here we have that a diagram illustrating the formation of a beach as the waves go into the bay and the energy of the waves drop, right? You tend to have the beaches now being formed as a result of the waves depositing materials within the bay. And that's how beaches are formed. So what do we want to know? The biggest mystery. Where do beaches get its sand? Well, beaches get their sand from various sources. For example, they can be washed into the sea by a nearby river. Beaches can also get their sand from nearby cliffs that have been eroded. Sometimes um, they are swept in by waves from sandbanks in shallow waters offshore. And also, they can be moved into or onto the beach by longshore drift. What are the factors then that influence the formation of beaches? All right, for beaches to be formed, there must be certain criteria to be met. One, the sand and sediment budget. In other words, then, it is the amount of sand that is being deposited as to the amount of sand being removed. So if you have, in order for beaches to be formed, much more sand has to be deposited than sand being removed. If you have more sand being removed than sand being deposited at the beach, then you're not going to have any beaches being formed. But if you have much more sand being deposited as opposed to the amount of sand, a very small amount of sand being removed, then you will have beaches being formed. And that's what we mean by sand and sediment budget. The direction of the longshore drift also explains the formation of beaches, because the longshore drift tends to move in a particular direction, and that is the direction determined by the prevailing wind. In other words, then the wind that is blowing from a particular general direction, and that wind will carry the longshore drift along the coast, and that is quite important for beaches to be formed. Longshore drift, otherwise known as oblique waves. Nature of wave action. The waves must be constructive, not destructive. Destructive waves do not create beaches, they only erode beaches. So the waves must be of a constructive nature, as well as the type of rock in the surrounding area that is suitable for the formation of beaches. In some areas you have limestone rocks and coral, and that will give you the white sand beaches. In other areas where you have volcanic or igneous rocks, they tend to give you darker types beaches. Some of the things that can cause sand to be removed from the beaches, unfortunately, sand mining, not a natural process, but the destructive waves can also remove sand from beaches, as well as the longshore drift can also remove sand from beaches. Let us now look at spits, tombolos, and bars. Let me say it again, spits, tombolos, and bars. Let's go! All right, now let us look at spits. Now, spits are actually linear deposits or lines of deposits of beach material attached at one end of the land or to the land, and it must be free at the other end or in the sea. In other words, then, a spit is a long narrow ridge of sand and shingle or rocks which is connected to the coastline only at one end. Good example of this is the Cocal Spit in Trinidad, as well as at the mouth of the Barima and Pomeroon rivers in Guyana. Now, in order for the spits to be formed, there must be certain conditions to be met in order for that to happen. For example, the sea must be relatively shallow. shallow waters are required for spits to be formed because the materials can easily be deposited and accumulated. All right. In deep water, tides will remove the materials so they won't get any chance at all to be deposited and let alone to be built up to create the spits. So it must be, the water must be relatively shallow or shallow enough for that to happen. There must be a good supply of sand and other materials to build up the spits. Yes, you need plenty of materials for that to happen. Lack of materials won't be able to cause the spits to be created or developed. The waves that are approaching the coast must approach at a particular angle to stretch out the spit. And these waves that are required must be that of the longshore drift in order to carry the materials further out into the sea or to stretch them out into the sea in a line or a linear pattern, if you want to put it that way. The sea must be fairly calm with low energy constructive waves. So constructive waves are needed. The sea must be generally calm, because if the sea is not calm and it has high energy waves, these waves will also wash away the materials and the spits cannot be formed. So this must be existing in that area over a period of time, a very long period of time too. So how are spits formed? Well, spits are formed in various ways. For instance, a spit can develop when materials are carried along the coast by longshore drift, which is the most common way, and is deposited where there is a sudden bend in the coastline or where a river enters the sea. A spit is also formed at the mouth of a river, which results in deflection of the course of the river. For example, the Oxford Ness River in England and along the Erin Coast in southern Trinidad. A spit sometimes changes its direction to form a hook or a curved spit. It develops when oblique waves change their direction, and this is usually due to the direction of the prevailing wind as well. All right. For example, Hurst Castle Spit in England. In time, the spit will be occupied by vegetation on the inner part of the spit, and on the inner part of the spit, you will have mud flats and salt marshes growing in there as well. Let's see what we mean by that. Okay, let's see what we mean by what we just said here now. Here we have two instances of a spit being formed. So we have a spit. This is the spit right here, the sediments being formed across a bay. Here we have the bay, or an opening or an inlet, and we have our spit stretching in front of the bay. That is a spit forming right there. A spit can also be formed at the mouth of a river, and that causes, and where the river ended here, you notice the river is ending out here now, because the spit actually diverts or changes the course of the river as a result of its formation in front of the river right here. All right. So due to the longshore drift, the spit is carried off the coast while still attached to it, but it's stretched out. Over a period of time, the prevailing winds causes the longshore drift to change course or to curve, thus over time creating what we call a curved or hooked spit. Now, because the water behind the spit is sheltered, what happens now, class, or what happens now, everyone, is that you tend to have sedimentation taking place. So you have materials being accumulating behind here, and this is what we call a mud flat. And in the mud flats, you also have marshes or swamps growing, all right, behind the spit. Here we have a photograph of a spit, and as you can see, it has changed into a curve. It's a hook spit. Here we have another one that also changed into a curved or hook spit. All right, everyone, now we're going to look at bars. So we just finished looking at the spits. We're now going to look at bars. What are really bars? Well, a bar is actually, just like a spit, a linear deposit of beach material running approximately parallel to the coastline. Now, the difference in a bar and a spit is that a bar is longer than a spit, to the effect that a bar can actually stretch from one end of the bay all the way to the next end of the bay. So when a spit extends from one end of the bay all the way to the next end of the bay, that is what we call a bar. And usually the water in the bay is no longer considered a bay. It's now considered a lagoon. All right. So some bars are offshore bars. They are not actually attached to the land, but they are out there in open sea, but parallel to the coastline. All right. Um, One good example of this is Miami Beach in Florida, and you can see several other examples being provided there. Now, over time, what happens is that, students, is that the offshore bar is eroded and the materials are transported towards the bay, and it will accumulate right at the mouth of the bay and trapping the water that is within the bay. So now you have the bar, and then behind the bar you have what was once the bay, now known as a lagoon, because it is trapped by the bar. So here we have offshore bars. All right. Here we have a photograph of an offshore bar as well, and right behind it is a narrow lagoon, a body of water there. This is Miami Beach in Florida. Nice little place. Yeah, love that place. But Miami Beach in reality is actually a bar. And right behind Miami Beach we have right there it is, our lagoon. Now, besides an offshore bar, we also have a bay mouth bar. Now, a bay mouth bar is actually a tongue of sand and other materials which extend across a bay. And just what I said earlier, a bar is basically a spit that has extended all the way across a bay. All right, especially when it is created in front of a bay. When the spit goes all the way from one end of the bay to the next and cuts off the water, that is what we call a bar. And the water that was once known as the bay now becomes a lagoon. All right. Now, some are formed by longshore drift. Others are formed when offshore bars are moved towards the coast by the wave action. Just like what we said earlier, when we just started looking at bars. So here we have our bay mouth bar right here. So it's basically our spit has now extended all the way across the bay and attached itself to the next end of the bay, following the longshore drift. So it is carried by the longshore drift all the way across the bay and attach itself to the other end of the bay. And inside here, we have what is called a lagoon. It's no longer the bay, it's now a lagoon. Over time, you tend to have mangrove swamps being formed inside here. So what is that? That is our bar. And right inside here is our lagoon. Within a lagoon, there are certain features that we need to take advantage of. For example, lagoons have no waves because it is sheltered by the bar. It is the water in the lagoon is not acted upon by the wind, so it is therefore no waves inside there. You tend to find mud flats or lots of mud and silt accumulating within the lagoon and on the lagoon floor. Vegetation like mangrove are also prevalent, or should I say, um, major in this kind of environment. And you may also find that um, the open water is replaced by wetland or swamp over a period of time because the lagoon is going to dry up and you're going to have dry land over a period of time inside that area. Now, we're going to show you how a bar is formed. So, first of all, let us look at the longshore drift. Here you have longshore drift taking precedence now. And here we have our sediments being transported and deposited in the direction of the longshore drift. This is what we call our spit. Now, as the spit continues to grow, you'll tend to have mud flats and salt marshes and swamps behind it. But look, the spit is continuously growing and it is extending all the way to the other end of the bay. Now it has attached itself to the bay. The spit is no longer called a spit, it's now called a bar or a bay mouth bar. The water that used to be the bay is now called a lagoon. Alright? And over time, you tend to have sedimentation, and even given enough time, you'll have dry land in there. So just for emphasis, I'm allowing it to repeat itself one more time. There you go. That's the bar, the Baymouth bar. And the water becomes a lagoon, no longer a bay. Tombolos. Now, a tombolo is formed when a spit connects the mainland to an island. So that spit is no longer called a spit, it is now called a tombolo because it is now connecting the mainland to the island. All right. And one good example of this is Scott's Head in Dominica. We can also add the Palisados in Jamaica as well. Here is our tombolo. Little known facts about Scott Head in Dominica. And here is our photograph of Scott's Head in Dominica. Here is the island. And that is our tombolo that has connected the mainland of Dominica to the island just off the coast of Dominica. Now, the thing about these tombolos is that some tombolos or most tombolas are not visible at high tide. They are mainly visible at low tide. Not many tombolas are that high. All right. But you do have a few tombolas that are actually always visible at either high tide or low tide because they're high above water level. But most tombolas, once in some, depending on what part of the world they are, they tend to be invisible or blocked off by high tide, but are only visible by low tide. Alright, so we have now come to the end of our lesson for today. I do hope that you all enjoyed it and you have learned something brand new and it was enlightening to you. Listen, just remember to leave your comments and you leave a like and click on that notification button and subscriber button, But outside of that though, I really appreciate you everyone that who have listened and observed what have been put forward today. I hope that it will be useful to you, especially if you are students who will be doing your CSEC exams in geography, or you weren't so keen on coastal features and it has opened your eyes a bit more. But even better than that though, if you are just somebody who just wants to edify your own edify yourself for your own edification, thank you very much for choosing this video. So please continue to love and work hard at geography and just make it a part of your daily routine. So take care everyone, have yourselves a great day.